Everyone. So today in this video, we'll see a very beautiful geometrical figure, the surface. So we'll define actually surface in modal language. I mean, using topology, we'll define what we mean by surface. So then we'll see some example. After that, we'll construct some surface, and then we'll try to write down the classification of the surface. So let me write here the definition of surface. So we need for this, the lecture, we need some prerequisite like few quotes on topology, like few definition and few facts from topology. But I'm assuming here that we are all familiar with those concepts. So therefore, I'm starting from the definition of surface here. So what do we mean by surface? So a topological space x comma tau. So x is a set and tau is a topology on x is called a surface if the following hold. So firstly, x is Hausdorff. So Hausdorff mean if you take any point in the space x to distinct point, you can find two disjoint open interval. The open interval separate that those two points. Then we call that is the Hausdorff space. And then we take here the next x is second countable. So Hausdorff imply that the if the topological space x contain infinitely many points, so then there are infinitely many open sets. So it guaranteed that the number of open set is huge. Basically. Now the second condition, x is second countable. So second countable mean second countable mean basically it has a countable basis. So countable basis mean it guaranteed that although the first Hausdorff imply it has infinitely many open set, but second countable guaranteed that we can control those infinity number of open sets. So that is second countable. So when we deal with the surface, basically these two property just we technically use sometime, but the main important property I'm writing here that is very important intuitively that for every point P belongs to X, there exists open set. There exists open set OP belongs to the OP belongs to tau, and open set let's say OP tilde open in R2 and a homeomorphism. Let's call it is psi of P from OP onto OP tilde. So this is definition of a surface. So see what I am trying to tell here. It is intuitively clear that if you have something like this, let's say we called this is x. Let's say we called as surface if it is second countable, and if we take any point here, then we can find a open set around P that is called OP, which is homeomorphic to open set in R2. The displaced open set we have in R2. This is called OP tilde. This is open set by the map side. So basically a surface means a topological space such that every point, you can find a neighborhood around that point which locally looks like the plane, right? So R2 means plane. So a very standard example is sphere. You take sphere, then for example, sphere mean you can think football if you take, then at every point, the neighborhood is very small place if you take, it looks like a plane. So in real life, we can realize it because we are living on a earth, and where we, if you look at your neighborhood, it is looks like a plane. So all time we do the plane geometry for our working purpose. But if you look at the global thing, then it is not the plane geometry will not work. So surface mean locally it is looks like a plane, okay, or open subset of RP, you can say that. So now, so this is the definition of surface. Now let me give you some example here. So the example basically, first example that comes in our mind is of course the plane. If you take any plane, then it is a surface. So I'm taking let's say this type of plane. So basically open plane, it has no edge. So yeah. Oh, okay. One thing I'll tell you here, there are one more definition of surface, the surface with boundary. But here I wrote here the definition surface without boundary. Surface means I will take the surface without boundary. Now, if you take this plane, I put here dot dot because I'm trying to say that we are not including the boundary. So this plane is this is a plane. We are taking this part. So then this is a surface. Of course, you know this is the first easiest surface. Now the next is basically you can take it is the first one, and then you can take here the sphere. You can take this is also a surface. Now let's say I'm taking the cylinder with the we are not including the boundary of the cylinder. If you include, then it will be a surface with boundary. But since in our definition we took surface without boundary, so this is also because if you take any point, then neighborhood actually looks like the open subset of R. Similar here, and all are actually Hausdorff and second countable because of the subspace of all are sitting inside R3. So the topology comes from basically R3. Now these are all the standard example which are the topology basically from R3, but later in the next chapter we see next example we see some surface basically that directly not inside R3 in some sense, but we can put them inside R3. So let me write here the construction of surface. Here, so let me take here the unit square, and then let's say we are identifying this edge with this edge. So then and let's say we are identifying this we take this way and it is this way. Then what we get? So basically, firstly we'll get a cylinder, right? So then you know let's say these two sides actually meet here. Now if you take this way orientation, here you have to take the opposite direction. So basically what you will get, so we'll get here so something I cannot put it here, so it will be here. So something like this. So here somehow you want to push it here, so basically like this. You put something like this, and here you this is called the Kalin bottle. So this is the Kalin bottle basically. So Now the question, is it a surface? The answer is yes, it is a surface. But this surface is, you cannot embed it inside R3 without intersecting. You have to make your hole, and you can go inside and attach this circular part with the proper orientation. So this is not embedded inside R3. So now the question, what do we mean by embedded? So let's say you have a topological space X and another topological space Y. We say X is embedded inside Y. There is a homeomorphism psi from X to Y, such that X to Y there is a one to one, basically bijective one to one map, such that X is homeomorphic with psi of X with it in basically. Then we call that X is embedded inside X. X is embedded inside Y. So you cannot find some map from here does not exist. There does not exist. Basically, this map psi from R2 to R3. This is a homeomorphism. You cannot find it from this. So you cannot embed it here. So this. So therefore, this is a surface, but it is not embedded in R3. But you can embed it in R4. So there exists phi, which is embedded in R4. So basically, this type of situation is called the quotient space. If you read the topology and few more quotient space concept, then you can deal this type of thing properly. And yeah, so now, okay, so basically, surface mean it is locally looks like a plane, right? Any point there is neighborhood looks like that. So now, okay, that's all. So now, yeah, there is a one more nice example that is called movia strip. So you take here a strip and take this orientation and take this orientation, then you will get here, put it here. So basically, it is a this. So basically this actually from here to here we are getting. So it is embedded in it. Right. So yeah. Now one more is torus. If you identify this and this, same orientation, this with this, same, and this with this, you will get first cylinder, then same orientation you have. So you just bend it and join those. It's true. Here it is. So basically this situation is correct. So this is torus and it is embedded in R3. Right. So now this surface and this surface is non-oriented. There is a concept of orientation. So if you take a surface and if you define and if you take anti-clockwise, the orientation, and if you move on the surface, it will remain anti-clockwise on the surface, then oriented. If it change, start with a position anti-clockwise and move along the surface, come back the place with the orientation change for non-orientation. For the movia strip, it will happen that if you start from here and you move to this side and here it will change, and when it's come back here, then orientation will be changed. So this is a non-oriented surface. So there is a nice theorem that if you take a surface, okay, then you can classify. So let's say we are taking all compact surface, then we can classify all compact surface. So basically, so compact surface. Compact surface means a compact topological space and it is a surface. Compact surface, we can divide it into two parts. One is oriented and one is non-oriented. So oriented surface list, if you check, first list will be the sphere. Then you know what? Then then it will be the torus, right? And then a double torus, and it has two holes basically. And then it keep going. So these are all list of oriented compact surface. And non-oriented compact surface means you will take a sphere, you know, you will take a sphere without it has no hole. Now take a movie strip. So you will take a movie strip. Then what you do basically, you know, you remove a disc from here, and it has boundary the circle, and then these two circle, this circle and this circle attach. Then so you take a sphere, remove a disc from the sphere, then the take the movie strip, attach there. So from circle of the movie strip attach with the circle here, the removing discs, then you get something. So this is called the sometime this notation. So this is called the connected sum. So this way you can create lot of oriented surface. Basically, according number of the hole, we can classify the surface. Compact surface, oriented, non-oriented, then the number, how many number of hole you have. So locally, whatever you can see, then you can give a homeomorphism from one to another, just looking at not counting the hole. So that is, big theory here. So yeah, there is a nice theorem that is open problem still, the Poincare conjecture. So you can read those. So yeah, that's all. So compact surface we can classify according hole and according orientation. Thank you so much. Good night. See you in the next video.